Present.
ಯಾರಾದ್ರೂ ಕೂರಿಸ್ಬಿಟ್ಟು ಇದು ಮಾಡಿ ಅಷ್ಟೇ. ಅಲ್ಲಿ ಮಧ್ಯೆ ಸರ್ US ಬಿಟ್ಬಿಟ್ಟು ವರ್ಕ್ ಆಗ್ತೀನಿ ಸರ್ PC US ಬಿಟ್ಬಿಟ್ಟು ಯಾವ ವರ್ಕ್ ಆಗ್ತೀನಿ ಸರ್ ಒಂದೇ ವರ್ಕ್ ಆಗ್ತೀನಿ ಒಂದು ಸಿಟಿ ಹೇಳ್ತಾರ ಅದಕ್ಕೆ ಪೆಂಟ್ ಹಾಕಿ ಒಂದಷ್ಟೇ ವರ್ಕ್ ಆಗ್ತದೆ ಯಾವ ವರ್ಕ್ ಆಗ್ತದೆ
ವರ್ಕ್ ಆಗ್ತಲ್ಲ
ಯಾವ ಕಾಗ್ತದೆ ತೊಗೊಳ್ಳ ಒಂದು ಕಾಗ್ತದೆ ಅದು ತೊಗೊಳ್ತೀನಿ
ಫ್ರಂಟು ಇತ್ತಲ್ಲ ಫ್ರಂಟು ಇತ್ತು
ಮತ್ತು ಫ್ರಂಟ್ ಆಗಬೇಕು ಸರ್ ಫ್ರಂಟೇ ಒಂದು ವರ್ಕ್ ಆಯ್ತು ಬ್ಯಾಕ್ ಯಾವ ವರ್ಕ್ ಆಗಿಲ್ಲ
ನೋಡಿ ಚೆಕ್ ಮಾಡಿ ಒಂದೇ ಎರಡು ಇರ್ಬೋದು ಅಷ್ಟೇ
ಎರಡಿತ್ತು ಸರ್
ಒಂದು ಮೂರು ಒಂದಿದೆ ಒಂದು ಕೀಬೋರ್ಡ್ ಇತ್ತು ನೋಡ್ತೀನಿ ಚೆಕ್ ನಿಮಗೆ ಲ್ಯಾಪ್ಟಾಪ್ ಅಂದರೆ ಅದಕ್ಕೆ
ಲ್ಯಾಪ್ಟಾಪ್ ಅಂದರೆ ಬೆಸ್ಟ್ ಸರ್ ವೈಫೈ ಏನು ಬೇಕಾಗ್ತದೆ ಇದರೊಳಗೆ ವೈಫೈ ಇರಲ್ಲ ಸರ್
ಇದೆಯಾ
ಇದಕ್ಕೆ
ಅಲ್ಲ ವೈಫೈ ಲ್ಯಾನಿದು
ಲ್ಯಾನ್ ಇದೆ ಸರ್ ಕಮ್ಮಿ ಫೋಟೋ ಹಾಕಿ ಅದಕ್ಕೆ ಈ ಮೆಷಿನ್ ತೊಗೊಂಡಿದ್ದೆ ಸರ್ ಇದು ನಾನು ಇದನ್ನು ಚೇಂಜಸ್ಕೊಂಡು
ಆಮೇಲೆ ಇದಿಲ್ವಲ್ಲ ಬರೀ ಸ್ಲೈಡ್ ಚೇಂಜ್ PPT ಅದಕ್ಕೆ
ಅದಕ್ಕೆ ಬೇಡ ಸರ್
ಅದಕ್ಕೆ ಲ್ಯಾಪ್ಟಾಪ್ ಇದೆ ಸಾಕು ಯಾಕೆ ಅಂದರೆ ಸಿಸ್ಟಮ್ ಯಾವಾಗಲೂ ಅಪ್ಡೇಟ್ ಈಸಿ ಆಗಿದೆ ಸರ್
Place is there. You want to replace me? Replace me. Place is there in front. These many are there. No, I can go. No, I know they are asking for attendance. We replace for 5 minutes. 5 minutes. That's why we are sitting here.
I, Shaktivel, Treasurer of IEEE PELS and IIS Joint SPC, and I am excited to be the host of today's program. So, first of all, I like to welcome all the guests, teachers, and all the students to this event. So now I request Dr. Kaushik Basu sir and HOD sir to take over seats on dais. So, a brief introduction about the program. The PELS Distinguished Lecture Program is among the most exciting offerings available to PELS chapter. Each year, PELS select some of its distinguished members to become a distinguished lecturer. This celebrates and honors their high achievements in the power electronics field while supporting PELS chapter activities with high-profile speakers for local chapter and section events. In addition to Distinguished Lecture Program, PELS also offers a Regional Distinguished Lecture Program to support members and local chapter in various regions around the globe. Available RDLs will usually give lectures in PELS local chapter and sections events within their region and in local language. Thank you. Now I request Dr. Balamurugan sir to address the gallery.
Very good afternoon to all. So, I welcome all of you for the IEEE PELS Regional Distinguished Lecture on modeling the switching behavior of wide band gap based power devices. So, today we have our distinguished speaker, Dr. Kaushik Basu. He is an associate professor from IISc Bengaluru. So, for this event, first of all, I would like to welcome all the staff members, so Dr. Premkumar, HOD, EEE department, and all the student members for the event. So I would also like to thank the support provided by the management for organizing this event. And also I would like to thank all the IEEE local chapter organizers for funding this event to become a great success. So I welcome you all once again. So now I request Dr. Premkumar sir to provide a tree sapling as a token of love to Dr. Kaushik Basu. So I'll also welcome Dr. Premkumar sir with a tree. Thank you.
Now I request Head of the Department, Dr. Premkumar sir, to address the gathering. So very good afternoon to all. It's indeed on this special occasion as we gather for another enlightening session under our first Regional Distinguished Lecture Program organized by IEEE PELS and IES student branch chapters. So we have with us Dr. Kaushik Basu, Associate Professor from IISc Bengaluru, who will talk on modeling the switching behavior of wide bandgap devices. So he'll be talking about the modeling of the complete the wide bandgap devices. So I would like to acknowledge our management, the Chairman, Vice Chairman, Secretary, Joint Secretaries, the Principal and all Vice Principals. Because of them only we could able to do all these kind of activities. So thanks for the support. And dear students, before starting this session, I would like to give you the glimpses or the perspective of this lecture, or why we wanted this kind of lecture. As you all know, nowadays, the power electronics is a very ever-growing field or the fast-growing field. And as of today, most of the power electronic systems are dominated by the silicon devices. That everyone agreed, right? So even some of the semester students are studying power electronic course, as well as some of the final students are doing some projects on power electronics. So you agree that most of the power electronic converters are dominated by the silicon devices. So now the time is slowly getting over. So now there is a new path, there is a new generation, called the wide bandgap devices, that is such as the silicon carbide, the gallium nitride, so and so. We have so many devices. Though it's still in the research, even some of the commercial devices also came out. So still it is in the research progress. So mostly in near future, you could see that most of the power electronic system will be dominated by the wide bandgap devices. So why? What's the need of wide bandgap devices? As you know, if you design any converters with wide bandgap devices, you see that it can be operated for the high capacity, high voltage, high switching frequency. Okay, so and with high efficiency. That's one thing what we wanted as a power electronic engineers. Right, so if you design any kind of a converters with this silicon carbide or silicon, in general we call it as a wide bandgap devices. So more in future, most of your converters will be lighter, smaller. Okay, so which will activate the fast charging for the EVs, right? So even for the greener technologies. So many opportunities are there, and also in not only this fields. Okay, so where it is going to affect, another evolving field is what electric vehicles. Most of all the electric vehicles, renewable system, aerospace, wherever we need a high frequency sources. Okay, so there these devices are going to dominate.
So once it dominates, obviously we need to have expertise, right? So in future, a lot of opportunities will come for electronic engineers. Even till today, a lot of opportunities are there for the electronic engineers. A lot of demand is there, but supply is very less. It's unfortunate, quite unfortunate. So in our department, we have taken initiative very long back. So we had to, focus on the power electronics as well. So compared to the other fields. So we have to motivate our students to focus on the power electronics. That's the reason we started this IEEE society as well, the PEL society, with a lot of motivation and a lot of objectives we have started. And under this PELS platform, so we got a chance from the IEEE to organize this regional distinguished lecture. So thankful to the IEEE team as well, and also the student branch coordinator, Dr. Balamurugan and his team. So thank you all. It's one of the very good lecture series, so it will be continued in future also. And also, you have to be proud that we have one of the distinguished lecture here, one of the distinguished expert here. Directly accessing Dr. Kaushik Basu is not easy, and we know that. So he is a quite busy person. So he involved in multiple projects. He is in discussion with a lot of industries. So directly accessing him is not easy. So today you have that opportunity to try to communicate or try to interact with him. Okay, try to ask questions. Okay, even if it is silly or whatever it may be. Okay, so try to interact with him. So I hope you will take this lecture series in a right spirit. Okay, so this will be continued. Thank you.
Thank you, sir. Now I welcome Nikita to give a brief introduction about the speaker.
Kaushik Basu received the BE degree from the Indian Institute of Engineering Science and Technology, Shivpur, India in 2003. The MS degree in Electrical Engineering from the Indian Institute of Science, Bangalore, India in 2005. And the PhD degree in Electrical Engineering from the University of Minnesota in 2012 respectively. He was a design engineer with Cold War India in 2006 and an electronics and control engineer with Dyno Power Corporation USA from 2013 to 2015. Currently, he is an associate professor in the Department of Electrical Engineering in the Indian Institute of Science. He has been an author and the co-author of several technical papers published in peer-reviewed journals and conferences. His research interests include various aspects of general area of power electronics. He is expertise in several fields such as PWM techniques for multi-phase and multi-level I-power motor drive, embedded system designs for power converters, I-frequency and I-power magnetics. Administrative and academic activities of Dr. Basu sir are Campus Coordinator Texas Instruments Scholar Program from 2019 till date, the Chair of IEEE IES Chapter of 2018, Founding Chair of IEEE PELS Chapter 2017. I kindly request Dr. Basu sir to take over the session.
Good afternoon and thank you for organizing this RDL, and I would like to thank Professor here who really did coordinate with me to make this happen, and also the HOD here, Dr. Premkumar, and I'm sorry I'm a bit late, but let's discuss. So maybe I can just get started. And also thank you for the kind introduction. So, you see the talk is a bit technical in nature. So before that, I would like to know is that, how many of you are BTech students here? Can you raise your hand? Mostly as BTech students, right? And did you do a course on power electronics? Yes. Many of you have done. Okay. So we'll try to keep it, easy, and we'll see. And you are encouraged to ask questions in between. So. You see that sitting there, I mean, right? Let's do that. Just try that. We can start from here. It's fine. Okay, this is great. Fine. No problem. All right. Okay. Good afternoon again. So we are in IISc. So wherever I go, I little bit talk about IISc. So IISc is a relatively, it's not a big university. It's relatively a small institution. We have about 500 faculty and about 5,000 students, and we work in all areas of science and engineering. We also are going to get medical school sometime soon. The work is going on, and yeah. So. And primarily, I should also say that we have mainly masters and PhD program at IISc in science and engineering, and the way to get into the program is you have to write GATE. Right? You have to write GATE, and we have actually two programs. One is the MTech program, and another is the direct PhD program. And if you already have an MTech, you can apply for directly the PhD program. And if you don't have an MTech, if you are a BTech student, you can also apply for direct PhD program. But you have to qualify through GATE and apply. And right now, in our group, we call it Sustainable Power Electronics Lab. In our group, we have about 9 PhD students, 3 MTech students, and 3 project associates. And we are mostly, 50% of our funding comes from government, DSCE, IEEE, and all. And then we also 50% of it comes from industry. Actually, now it is, I think, more than 50%. It is from industry. So we work with people, big companies like TI, Delta, and then medium-sized companies like SR and also startups like Harvard. So from our lab also we have multiple startups which have been incubated in IISc. So and what we do, so what we do is we work in the area of power electronics. So mainly few hundreds of watt to few hundreds of kilowatt. See, the problem is that it is so stuffed here. If you talk in the back, you cannot listen to me. Right? Usually, I have fight with students talking in the back benches in my class, no problem. But here, if you talk, everybody will listen to you because of the reflections. If you have a question, you can ask me. So the thing is that few hundreds of watts. So before I go into that, I will tell you, give you some idea about what is watt and kilowatt and all that. So see, typically your phone charger, right, about 20 to 30 watt, and your fridge will be few hundreds of watt to close to a kilowatt. So at our home, generally the power that is being consumed is about a kilowatt, right? So now you have an idea of what is watt and what is kilowatt. So we work from few hundreds of watt to few hundreds of kilowatt up to megawatt. And what makes us different from generally others is that, we are of course in academia, we do academic research. But most of our research is translated. I mean, we do technology transfer to other companies, which actually take it to a product. So today, that is what I'm going to talk about. This wide bandgap devices. The work was done by two of my students. One is Dr. Shomi, he has graduated and he is working in Delta Electronics. And the other student, Manish, he just defended his thesis and he got the degree last Friday. And he is co-founding a startup based on this work that we are going to discuss in IISc. So I think, see, this is a picture of a buck and butter. I think all of you have seen this if you have done one power electronics course. So in buck and butter, what happens is that you make from this DC, you make another smaller value of DC here, right? Using a switch and a diode, right? Now, when the switch is on, then this receiver's voltage is here, and this EA voltage is VDC. And when it is off, current flows to the diode, and this voltage is here, right? And the width of this and what we call the duty cycle of this can be changed to change the average voltage. The DVDC is the average voltage, right? Which is the ratio of the on time to the switching cycle time, right? TS. So by changing that, I can change the average voltage, and then you have an LC filter, which is a low pass filter, which will take out all the high frequency, and the average will come at the output. So say this is 100 volt, and you want 25 volt here. What you have to do is you have to keep the 1 quarter, you need to keep it on. Right? So if say the switching period is 100 microseconds, 25 microseconds you have to keep it on, 75 microseconds you have to keep it on. The average will be 25 volt, and that will be filtered. So whatever extra is there will be filtered by this LC tank, and you will get the output. So this is how we basically do power conversion, and this is called pulse width modulation. By modulating the width of the pulse, you can change the voltage or you can control the output voltage. But of course, in this converter, if it is a 100 volt input, you can make only 0 to 100. So when it is 0, the pulse width will be 0. All the time it is 0 only. And when it is 100, it will be always on. It is just 100 volt you will apply. So your voltage will be always in between 0 and 100. But now how we do this? So the main thing here is, other than the filter, is this switch, right? So this is an electric switch. So there is a voltage across this switch and there is a current through this switch, right? So when the switch is on, what happens? it takes current and it is acts as a short circuit. So the voltage is 0, right? Across it the voltage is 0, right? See, I can hear you. If the voltage is, when it is on, voltage is 0 and it takes current. And when it is off, it blocks the full voltage. You can see the voltage here becomes the diode conducts, the voltage becomes the DC bus voltage. When the switch is off, right, that time the voltage across becomes the DC bus voltage. And when the switch is on, the current is equal to the inductor current. Whatever that current is, it is equal to that current. But the voltage is 0. And when the switch is off, then the current is 0 because the current flows through the diode. So the loss in a two-port element is the voltage into the current. That is the power loss. So now if you see in this idealistic waveform, voltage into current, if you do multiply, it is 0 in this. Correct? So this is fantastic, right? And we also understood that if you want 25 volt here, okay, fine. You say if it is 100 microsecond, 25 microsecond, you keep it on. The rest 75 microsecond, you keep it off. Correct? That's what we understood. But we can do the same thing. Let's say we can do this period 10 microsecond instead of 100 microsecond. And we will keep it for 2.5 microsecond. Then also I will get 25 volt. Correct? So once I am taking the period 100 microsecond, another time I am taking the period 10 microsecond. So 100 microsecond is how much? It is 100 kilohertz. And 10 microsecond is, right, lower. Sorry, it is higher, right? No, just a second. 100 kilohertz, 100 kilohertz is 10 microsecond, right? Because 1 megahertz is 1 microsecond. And 100 microsecond will be 10 kilohertz, right? So now the question is that whether you want to switch this at 10 kilohertz or you want to switch this at 100 kilohertz. Both of them will give you same 25 volt at the output, correct? Now the thing is that actually we want to choose the higher switching frequency. Why? Because see, look, there is a filter here. So L and C, there is a filter. It is a second order filter. What is its cutoff frequency? 1 by root LC. That is the resonant frequency of that tank, right? So what this guy should do? This guy should act as a low pass filter, right? So the voltage here, the VAN voltage that is here, that voltage, if you look at the spectrum of that, right, the periodic waveform, if you look at its Fourier series, how many of you have studied Fourier series? All of you have studied, right? So there is a DC component which is 25 volt, and then there is harmonic components which are at switching frequency and its multiple, right? So now so for example, if it is switching at 10 kilohertz, there will be a average voltage that is 25 volt, and then there will be harmonic components in that whole voltage which is damping like this. It will have components at 10 kilohertz, 20 kilohertz, 30 kilohertz, and so on and so forth, right? But now what you would like is to, cut off or stop those high frequency component, and you want only the DC to pass through. You want only the 25 volt to pass through, right? So that means your filter, low pass filter corner frequency should be below 10 kilohertz, right? So maybe it is at 1 kilohertz. You have to put, so that all the switching frequency components will go away. Now, if the switching frequency is at 100 kilohertz, then that corner frequency can be moved to 10 kilohertz now, right? I can increase that. And if it is 1 by root LC, so if you increase that, L will reduce, C also will reduce. So that is what will happen. So if you switch at higher frequency, the size of the converter will become smaller. So you must have seen that nowadays that you see this fast chargers, right? In Amazon you will find GaN based fast chargers which are 60 watt but still this size, right? So high power but small in volume. Why that is happening? Because we are able to switch them faster. So the thing is, then you will say that, okay, then why stop at 100 kilohertz, right? Why not go to 1 megahertz, 10 megahertz, so then it will be even smaller. Now the problem is that actually the switch that we use, that switch is not ideal, right? So there are two things. One is that when the switch is on, the voltage is actually not zero. So I am showing it here 0 when the switch is on and carrying the current I0, or that is the load current. There is a conduction drop is there, and the switch appears. It's a MOSFET, right? It appears as a resistance. It's a ohmic, right? And also, when the switch makes a transition from on to off or off to on, right? So you see, if it is going on to off, the voltage, current is becoming from high to 0, and voltage is becoming from 0 to high. Correct? So when you see here, voltage into current, and here the voltage into current is very small. Actually, when the switch is off, this is 0, really 0. Leakage current is usually very small. But when the switch is making this transition from non-zero voltage to 0 voltage, and from 0 current to non-zero current, there is an overlap between them. And that overlap causes a blip in the VI product. And there is an energy that is being lost. So the energy that is inside this, in this area of that triangle is the amount of energy that gets lost. So the power loss means, see, if it is 1 millijoule of energy, right? So 1 millijoule of energy. So the thing is that if you switch it, right, at 1 kilohertz, the loss is going to be 1 watt, 1000 into milli, right? 1 watt loss will happen, right? If you switch at 1 megahertz, it is going to become 1000 watt, 1 kilowatt loss will happen, right? So maybe this converter is only for 20 watt. So you cannot just burn 1 kilowatt for that, right? So the limit, so actually the loss is frequency into this triangle, correct? Now if you increase the frequency, it will go up, correct? So this is called switching loss. So now what happens is that if you take the previous generation of semiconductor switches, what we do, we use here what is called power semiconductor devices, right? These are basically transistors, right? So MOSFETs, I think all of you have studied MOSFETs, right? So the MOSFETs has 3 states. Remember, one is cut off. When the threshold voltage is below, it is cut off. When the threshold voltage is higher than the gate source voltage is higher than the threshold voltage, what happens? It turns on, right? And then you have 2 regions. One is what we call saturation region. In the saturation region, both the drain source voltage and drain current are high, and we use our analog electronics in saturation region, if you remember, right? All our power amplifiers and all our amplifiers, radios and all of that, right? They are made in, all the op amps, right, are made in saturation region. But when you go to digital electronics, there is another state where you use it like a switch, on and off, right? So in that, what happens is that your drain source voltage falls to such a small value that it is almost like a short circuit, right? It acts as a switch. So in power electronics also we use the MOSFET in 2 regions, either cutoff or ohmic region, right? Now this changeover, and so this is based on silicon technology. Now what happened is, around from 70s, power MOSFET became possible at low voltage, and around 80s there were some breakthroughs, and we have been able to make power MOSFETs up to a voltage of 650 volts, and that is when all your UPS came in the market. Around 80s the UPS appeared in the market, right? When the load shedding happens, you can take out the battery and put an inverter and you can turn on your light. So that was the biggest power electronics thing that was around in 80s and 90s. But we could not make devices at higher voltage. Electric fans also started coming, where WBG-based fans started coming. But then what happened is, about 90s, there was another breakthrough, and that breakthrough was we could able to make these MOSFETs at high voltage. That is about 1200 or 1000 volts. And that is where the motor drives came, and that revolutionized. You had traction, railway came, electric railways in 90s because of IGBT. And interestingly, the IGBT was discovered by Professor Jayant Paliga when he was working in GE in 90s, right? And he was from Bangalore, right? And actually, unbelievable amount of energy has been saved, and unbelievable amount of technology was possible just simply because IGBT was invented. None of your solar, none of your EV traction, none of your industrialization of motor drive saving huge amount of energy would not have been possible if those discoveries did not happen. Of course, power electronics worked along with that. So this is the state of the art till we went up to the last decade, 2010. Up to that, it is all IGBT and silicon. At high power, it is IGBT. High power means 3-phase power, 10 kilowatt, it is IGBT. And the lower power, all your mobile phone charger and all that, it is silicon MOSFET. That is the technology. A little higher, you call silicon super junction MOSFET. Now, the thing is that if you look at IGBT or silicon MOSFET, they switch. That switching time, right? So if you look at that energy loss in that area of that triangle, now the peak of that triangle depends upon the blocking voltage and the current. That comes from the circuit. How much is your input voltage, DC bus voltage, how much is your load current, right? But the area also depends upon the base, right? How much time, how fast the switching happened. How fast the current went down, how fast the voltage went up. So if that base becomes smaller, then also my energy will become smaller and I will be able to push to a higher frequency. That is the whole idea. So if you take the IGBT takes hundreds of nanoseconds to switch. Hundreds of nanoseconds to switch. MOSFETs at low power also in that tens of nanoseconds to hundreds of nanoseconds. They take time. Okay. Now the thing is that now from 2010 we have two new technologies. One technology, I have picture. So the two new technologies have come up. One is at high voltage where IGBTs are used. There with IGBT there is a new device has come that is called silicon carbide. And the silicon carbide, the material is basically silicon carbide MOSFET, right? And they can switch in tens of nanoseconds compared to hundreds of nanoseconds, right? And what did that enable? What it enabled is your electric bus and truck. We were unable to do that with IGBT because if you do it with IGBT, the switching frequency has to be lower than silicon carbide. And then if your motor traction drive and your charger, onboard charger will be so heavy that it will take up a lot of space. So if that takes up a lot of space and a lot of weight, what will happen? Per battery charge, the amount of distance you will be able to go will reduce because it is adding to your payload. Correct? See, if your battery becomes just the weight that it can only carry itself, no person can go and sit there, right? So that breakthrough that this brought is electric traction, right? That is what the IGBT is doing right now. And so if you build an IGBT based converter, theoretically it should become 10 times smaller. If it was like this, it should become like this, right? Now, in the low power, we have another candidate, and that is called gallium nitride, which is competing with silicon MOSFET. Now, gallium nitride, though it started, as you see in this picture, started coming from 2015, around that time. Still the technology has not been stabilized. It is happening as we speak. But 2015, when we started this work, silicon carbide was also in its quite nascent stage in the commercial implementation. So, when we started this work, when Shumiprata came to do his PhD around 2016-17, people were asking in industry one question. They're still asking. But the question is that if I just replace IGBT in my design with silicon carbide, is it possible to make the, say for example, I will tell you a solar inverter, right? With IGBT, if it is a 50 kilowatt inverter, usually 50 kilowatt will be something that, in a college or somewhere, if you have the rooftop, it will be like 50 kilowatt. And remember, 50 kilowatt means 50 homes. So if it is a 50 kilowatt with IGBT, keeping the losses within 2%, IGBT can switch about 10 kilowatts, right? But if I replace with that with silicon carbide, the idea is that silicon carbide you should be able to go to 100 kilowatts. Correct? And that means my filter and all will become smaller. Or if I reduce, if I don't switch at 100 kilohertz, if I switch at, say, stay at 10 kilohertz itself, then my losses will be also 10 times small. So I may not need any heat sink. Right? Then also my converter will become smaller. Right? But in 2015, when people started doing this kind of thing, they will put silicon carbide in the converter and they will see that no, if they try to switch it fast, they see a lot of ringing and devices are failing. So what they will do, they will slow it down and they will switch it like IGBT. Then there is no benefit for that, right? So this was one problem. And then there was another problem is, see, the thing is that whenever you have to select a device for your work, right? For your, say you want to build a converter, there are multiple vendors like Infineon, Microchip, there are so many companies, Semicron, they make the same devices. So how do you know which device to use? It is not just a matter of cost. Cost is important. Supply chain is important, but beyond that, how you know that which device will work for you? So what you have to do is, you have to do some calculation. Say for example, you are making an inverter and I told you that your losses cannot be more than 2%. So then you know the loss, right? Then if you, from the device data sheet, if you give this operating condition, the DC bus voltage and the current, you will be able to calculate that E on and E off, right, from the data sheet. And if you put that here, you can see that if I want in a 10 kilowatt inverter, if my loss is 2%, how much is that loss? 10 kilowatt. How much is that loss? 200 watt. 2%. 10 kilowatt, 1000. So 1000 means 1000, 10 to the power of 4. So I divide it by 100, it is 100. So 100, so 200 watt is my loss. So the P is 200, right? And then I will put that number here and I will check how much is the switching frequency I can go, right? That is a design calculation people do, right? And maybe say you know that you want to have your switching frequency at 10 kilohertz. Then if you do this calculation, you will see that it is not matching, correct? Then what you have to do is you have to go for another device which has a lower E, so that at 10 kilohertz still you can get 200 watt loss, right? So you need to do a calculation. Now the question is that this calculation, that method that people use in industry, there is a simple method called linear, extrapolation kind of method, linear scaling technique we used to call. Surprisingly, what people found is that that technique which works in IGBT does not work in silicon carbide. And they have to do some experimental method or something to do it, right? So when we started, when Shumiprata started doing this work in 2017, we were asking two questions: that why you see all those ringing and all of that, and why you are unable to actually estimate the losses, correctly and why you have to actually do the experiment. Right? So this is the background at which we started doing the work. So now what I'm going to do is, it can get a bit technical. I will not go that much technical. I will keep it little bit simple, right? And I will tell you what actually we did and what we did found and what is our startup based on, right? So what happened here is that actually if you see these power electronic converters, I think you guys have studied the mark and boost, right? So what happens is that, see, when the current is in this direction, see, there are two devices are there, top and bottom. When the current is in this direction, actually this switch and this diode conducts, right? Like the buck converter. And when the current is in this direction, it is this switch and this diode conducts. This is the boost converter, right? Now buck is unidirectional from to here, power flow. Here the boost is unidirectional, power flow is from here to here. So now if you want a bidirectional converter, you have to put two switches like this. So that sometimes when the current is in this direction, it is buck. Sometimes when the current is in this direction, it can operate as a boost. And you get a bidirectional. So all your battery chargers needs to be bidirectional to certain extent. Because then only you can extract also the charge from the battery. And you can also push the charge into the battery. Right? So this technology is called vehicle to grid, V2G, you might have heard. Right? So now the thing is that we need to actually, so now the thing is that how to answer that question, how to find out that loss E on and E off. So it's basically it is the product of the voltage and the current when they are making a transition during the switching. How the voltage is changing, how the current is changing. If you find those two, you multiply them and you integrate them. You find out the loss, right? So the thing is then what you have to figure out, see in this textbook picture, it looks like straight lines like that. But in actual reality they are not straight lines. There is a complex curve. They go up and go, one go up, another go down. So the question is that how can I figure that out? That is the problem we are answering. So now one question that I have talked about all this with respect to buck converter, correct? Now in power electronics you have so many other converters, right? So there are thousands of converters. In research there are infinite number of converters. How will you, do you have to do this exercise for all converters? The answer is actually not. And it turns out that the most of the power electronic converters, you will find out this block of a half bridge. Okay. This is a half bridge where there is a top switch and there is a bottom switch. Two N-channel MOSFETs are connected like this, right? Which can be operated either as a buck or a boost. Right? So if you actually study how the voltage and current change during switching in this converter, you have studied what happens in all other situations. That is the fundamental idea. And also, what happens is that it is either buck or boost. So the switching always happens between the switch and the diode. Right? When the current is in this direction, it is basically this switch and this diode. When the current is in this direction, it is this switch and this diode. Right? See, it took us also a long time to understand all this, but I am telling you it looks so simple. So actually if you study this circuit with just one switch, one diode, that should be enough for you to figure out how the switching loss will happen or the calculation that you would like to do. And another thing is that you have to take this as a voltage source, and this inductor is a large current carrying element, right? So inductor current change in a buck converter during the switching period, right? It's a 10 microsecond or 100 microsecond. Now in nanosecond, in 10 or 20 nanosecond, inductor current cannot change. 10-20 nanosecond inductor current cannot change. And you know that L, di, dt, right? that is the inductor current, no? Voltage across that inductor. So if your delta T is very small, your delta I also will be very small, right? So change in the current will be very small, and you can actually effectively model this as a current sink or a current source, right? So what we did is we actually studied this circuit. There is a switch and a diode, and there is a current sink here, which is modeling the load, and we are actually studying this circuit. And we will switch here, and this will work as a half bridge, and we are going to observe how the current and voltage changes. Okay? This is what essentially we are going to do. So it is as simple as, from the power electronics perspective, it is as simple as the buck converter, nothing else. And what you would like to estimate is that if I give you the datasheet of this device, right, I should be able to tell you, given this current where you are switching and the DC bus voltage that you are switching, if it is say 800 volt DC bus and you are switching at a current of 5 ampere, and if you give me the datasheet of that MOSFET, I should be able to tell you how much is that energy loss will happen. Correct? That is what, if I know the energy loss, I can multiply it with the frequency and I will get the actual loss. And usually I have a loss budget. And the loss budget and this energy will tell me what is the frequency I can go. Right? And the frequency is a key design parameter of power electronic converter, which resides in size. Actually, we have been all through this revolution, at least in the personal computing. If you just think 10 years ago, a laptop charger seems to be this big, and now you see it has become so small. There's a tremendous technology improvement that has happened, and all because of this, what is going on here, right? So what we have to do is, we will be studying this, and we will find out how voltage is changing and the current is changing, and then we will be able to integrate that and find out the energy loss during off and on period. And then these are also important. Say for example, I told you, there will be some ringing. That is what people are seeing. So now if there is ringing, those ringing will create EMI noise. Say for example, if silicon carbide converter is switching, you take your laptop you will see that it is catching a lot of interference, right? You will not be able to work on your laptop if the EMI is not properly shielded, right? Even if you think about this, say you are on a car and you want to use your mobile phone, but if there is a silicon carbide converter switching at 100 kilohertz and no EMC is taken care, you will not be able to use your phone, right? So there are a lot of technology going on there. Now, so we need to know that, how fast is voltage current changing, and also what is the frequency of this ringing, and also there is overshoot. Voltage overshoot is there. You can see that the voltage is going to the receiver's voltage, but there is an overshoot. And if this overshoot goes higher, it can kill the device. Right? Now what has happened is that because of all this happens, when you have a very high switching frequency, right? Switching transition is happening with silicon carbide, all these things happens. And it turned out that it has become very difficult for people to make converters with silicon carbide. But now it is little better. But I would not say that everybody can do it, right? So that is why you see, even though the technology is much superior, there is only 5% penetration of silicon carbide replacement has happened with IGBT, right? Because it requires advanced level of understanding to design converters using wide bandgap devices. So our work is here to simplify that process, or figuring out what a design engineer is going to do or how to solve this problem. And this problem is still not fully solved in gallium nitride. People are working, we are working, we have some solution, but things still very difficult. So I will now very quickly tell you what we do here. So what happens is that the MOSFET here, this MOSFET here can be replaced with the equivalent circuit. I think all of you have seen this circuit. When you study your MOSFET, there is a channel current which is the function of drain source voltage and gate source voltage. And then when you study the high frequency model, see, when the gate source voltage is below threshold, it is cut off, channel current is 0. When it is, then when it is beyond threshold voltage, it will go like, the square law is there, right? VGS minus V threshold whole square. You've seen that formula in your analog electronics, right? And then also when you studied the high frequency circuits with your high frequency response of amplifiers, you have seen this parasitic capacitances that comes in the MOSFET. These are because of the diffusion. These are called diffusion capacitances. So I hope it is still being taught, right? The MOSFET models and all that with NEP, or it's all gone. It is still taught, right? So the thing is that, but here what happens is few things different here. One is that this relation between the channel current and gate source voltage, drain source voltage is not that simple. If you remember, your these curves, one is ID versus VDS, another is ID versus VGS. These two curves are there, right? And these capacitances are also, this is constant, but these are nonlinear functions of the drain source voltage. And because these terminals are there in the MOSFET, right? At high frequency, those terminals also act as an inductor, right? Because if the current is changing very fast, DIDT is so fast that a small L will respond with a voltage. LDIDT will not be very small if the DIDT is very fast. And usually we are talking about here hundreds of ampere switching at few nanoseconds. If you think about, it's a next generation stuff that we are talking about here. Now, what happens is that, so those inductors also come up in the lead. So this is the IDVDS curve that you have seen. See that when you study analog electronics, you remember, this is the drain current, this is the drain source voltage. During cutoff, you are on this line, drain current is 0. When the gate source voltage is below the threshold voltage. And when the gate source voltage is above threshold voltage, you have this, right? For a particular gate source voltage, above threshold voltage, you have this graph, right? More gate source voltage, for a given drain source voltage, you have a higher drain current. Remember? This is what you have seen, right? But here what happens, the same thing happens here. This is the cutoff region, this is the ohmic region, and this is the, the saturation region. But what happens here is, because the geometry and the device structure is quite different from the signal silicon MOSFETs to power silicon carbide MOSFETs, the equations comes out to be much more complex. It is not that simple. So then what do we do if we have to use that circuit model? I need to know the functions. If you tell me drain source and gate source voltage, I should be able to compute channel current. Now for that, what I need to do is I need to figure out the different coefficients here, which I do not know. Say for example, I need to know the threshold voltage here, Kp, theta, these are all that kind of constants. These are we call parameters. So now one way to do this is that you can do a curve fitting, right? You have these curves coming from the datasheet, right? Datasheet has given you these curves through curve tracer. Then you can take those points and then you do a curve fitting, and that curve fitting will give you those parameters through an optimization problem which will minimize the error, right? I think all of you know basic curve fitting, least square. The entire machine learning is basically curve fitting business, right? Not like that, but almost like that. Regression analysis. So happens this nonlinear capacitances are also like this, right? So what happens is that if you give me the data sheet, I can actually find out all these parameters, and then I will know all these elements in the circuit, right? Though these are all nonlinear, the channel current is nonlinear, these capacitances are not fixed; they are function of the voltage, complex nonlinear functions of voltage. So we do that. I will skip this. This is for gallium nitride. This also I will skip. And what happens is that this is your half-bridge circuit, right? So the devices, the MOSFETs, you can replace it like this, what we just discussed. And then also you have circuit parasitics, right? Now, what happened in IGBT and silicon carbide, IGBT and silicon MOSFET, this circuit parasitics, so what circuit parasitics will see, if you connect out to one wire, that wire is not a zero impedance, right? If you pass a high frequency current, that wire has an inductance. That wire will appear as a voltage drop, there will be an LDIDT. Similarly, when you have PCB tracks, right, you have one metal, FR4 material, that is dielectric, another metal, right? Now, if the frequency of the voltage is very high, it will act as a capacitor. C dVdt. If the dVdt is very high, C dVdt, even the capacitance is in nanofarad, C dVdt product will be few volts or few tens of or hundreds of volts, right? Now, because here compared to silicon in wide bandgap devices, we are switching much faster. All those circuit parasitics which were silent in case of IGBT or silicon MOSFET are now prominent. They are coming out, right? So that is why the techniques that was used before cannot be used here, because here not only you need to know, understand how the voltage and current changes during switching, not only you need to know the parameters from the data sheet, you also need to know this circuit parasitics that is there in your actual circuit. So now if you put together all of this, then it becomes like for our electrical people, the once I know the circuit, now I can apply KVL and KCL, and I can find out, write down the equations, and then I can solve those equations, right? And if I solve those equations, I will be able to find out. So for example, this is kept always on, so that is your diode, and here you are going to switch the gate source voltage here, right? So if you switch it, you will see that how the differential equations of the KVL KCL gives you, and then you can solve them, right? So this is what, okay. Now let me just tell you a little bit also, you know that, but how I know these capacitors, right? So one way is that if you, I don't know whether you have designed a PCB, printed circuit board. So if you design a PCB, you can actually take those PCB files and give it to a numerical package like ANSYS, and from there you can extract these lump parameter capacitors and inductors. Right? This is one way. Another way is also you can experimentally also measure. So we have figured out some ways to measure it experimentally. I may not go into the detail of that, but I will come to this. So it becomes basically, you know, a set of differential equations. So there will be differential equations you try to solve. These are basically the voltage across two nodes and the currents through various elements. Right? This is a circuit you are solving. It's a differential equation circuit because you have inductors and capacitors. And what is different here is that you also have capacitors which are function of voltage, and you have also channel currents or dependent current source which are nonlinear function of voltage and current. So that makes the analysis nonlinear compared to a regular RLC circuit. Right? So very hard to solve them by hand, probably not possible. So one way to do that is you can do it numerically. Numerically you can run some finite, you know, difference method or Detta-Paramgay-Gupta method or something, and you can solve. Right? So now I'm going to skip all this and skip all this, and I will show you this. So you see here there is a circuit. It's a silicon carbide MOSFET which is 800 volt and 30 ampere. This will be a MOSFET probably used in your solar inverter, or it would be in your car. If you have a EV, inside the EV traction motor, we have a silicon carbide MOSFET like this. So if you take this MOSFET, and what we have done is we have switched it. You can see it is 100 volt. So this is the turn on, right? The device was blocking 800 volt here, coming to 0, and here the current is going from 0 to 30 ampere. Right? Now you see, now measure, and this, you see this is happening in few tenths of nanoseconds. That's the bottom, the time period. Now measuring something like this also requires lot of expertise and experience. So it took us long time, and I think you know there is a company called Tektronix. We also work with them to come up with new generation of test equipment so that we can see some of these things. Right? So we evolved together. So we have used some of the Tektronix probes. we talk to them like, okay, I cannot see with your probe, this is limiting the bandwidth, or your capacitance of your probe itself is so high that I cannot see this capacitance. So then they go back. So there is a new technology that they have come out with called ISO2 probe. So where this high voltage, high frequency, but isolation is there, where you can actually measure this kind of response. So this is what we have measured, and the dotted line is what came from the numerical simulation, which we obtained by using the datasheet parameters and also the parasitics that we have measured, and then we have put it on the circuit model and then solved that circuit model numerically, and we have matched. You can see that we have a good match of this. So essentially, that is what is the work that is being done. Now I will go and not discuss all this. I will come to two things I will teach you. So now we have a tool, and that is what the startup my student is doing. So we are looking for people in the startup. So if you are interested, you can send your CV. So now in this, what happens is that right now we have a web-based tool which is connected with ChatGPT. So user has to give the datasheet number. Every datasheet MOSFET has a datasheet number. So you give that number and you give your operating point, 800 volt, 700 volt DC bus where you are operating. You have to give a range of current. Right? If you give this, and what is the gate resistance you are using, what is the gate voltage swing where you are turning on or off gate, right? What is the voltage you are applying? 0 to 15 volt, 0 to 12 volt, or minus 6 to 12 volt, or what you are using. If you give that, then what happens is that this tool which is behind ChatGPT, it will go and search on the different vendors' website, and also it will go, DigiKey is one of the vendors that supplies these components. It will go search, and from there it will pick the data sheet. And then we have another tool, an image processing tool, that will go and from that datasheet curves, it will find out where are those IPVDS curves and the capacitance curves. It will go and then digitize that data. And once the digitization of the data is done, then we have a Python backend, which will basically then do the curve fitting. And then I will ready with solving those differential equations. And then we will numerically solve those differential equations and give you the data. So finally, you will get, so this is the datasheet curves, and these things you have to give it to it, and then it will give you the output. I think that picture is not there. Right? So this is what we are doing. We are currently working with Infineon, Microchip, and many other vendors to validate our data, right? Validate our software. So now I will discuss one applications, and then I will stop. Okay. So now what did we do with that? So all of this is good, right? So these are all design tools. So did we do a design to make that tool? So now if you see in the EV, what is getting electrified really, if you have noticed, is two-wheelers and three-wheelers. Mostly, cars are less. And actual numbers are that, out of which 6% only has become electrified of all ground transportation. I mean, four-wheeler, two-wheeler, three-wheeler, bus and all that. And out of that 60%, 80% is two-wheelers. And out of that two-wheelers, 90% are scooties, that is 100cc, right? You don't see much bike. There are some ultraviolet and all there, but very few. They are quite expensive also, right? So, and mostly those scooties that you have seen, they are about 100cc, 10 kilowatt, that kind of power. There are reasons for that, I am not going to go in that. Now, what happens is inside the scooty, there is a 3 kilowatt hour battery. Okay? So, and that battery can take you about 90 kilometers, 60 kilometers actually, 90 kilometers. So, one charge if you give, you can go about 60 kilometers. Now the thing is that one problem is that if it is a gas vehicle, you can put the petrol in few seconds, tank gets filled, right? But to charge the battery it takes time. Now it is 3 kilowatt hour of energy. 3 kilowatt hour. So if I charge at 1 kilowatt, how much time it will take? 3 hours it will take. Now what happens today, they have gone like, portable, like your laptop. The charger is not inside the laptop or not inside the phone. Battery is inside. Here also the same thing. So they give you a portable charger, which is not really portable, which is about 2 to 2.5 kgs and which is about 600 to 700 watt. And which is about 3 liters. Now you know what is 3 liter, right? That big Pepsi bottles. Do you think it is portable? Not really. And how much time it will take to charge? 700 watt. You take, 600 watt, you take 3 kilowatt, right? It will easily take 5 hours to charge. Now, there are also fast chargers, you must have seen. In the EV stations, charging stations, it is there. Somewhere in the malls, it is there. You will see Aether, Vita, all of them has this. Ola has this big charger, which is like one mount big charger, where those are 3 kilowatt charger. So those 3 kilowatt charger, how much time it will take to charge? 1 hour, right? 1 hour it will take. So now you have to find out from your phone where is the nearest place that 3 kilowatt charger is there. You have to go and stand there in the parking lot of a mall for 1 hour, then charge it and then go. Very, very inconvenient, right? So, and that is one of the main reason why EV is not taking off. One of the reason, big reason, that it is not that flexible, that refueling is a big problem, and time it takes to refuel. So the question is that what if, so that 3 kilowatt charger is big, right? So what if I can make, and that 3 kilowatt charger is made with silicon MOSFETs. But what if I change those silicon MOSFETs with gallium nitride and increase the switching frequency? So typically they switch the PFC or the front end AC/DC. So we are talking about a charger 230 volt 50 Hz 3 kilowatt, which is charging the 48 volt battery, right? So now instead of few tens of kilohertz or 100 kilohertz, what if I can go up to 1 megahertz? But still efficiency remains same because that E has become smaller, correct? So that the same loss I can go up, right? So this is what you see is a charger that we have made. It's a POC as a part of this project where we have made this charger. This is this size. Okay, 3 kilowatt fast charger. It is going to be about a kg, and we are targeting it to become something like you have seen those speakers, no? Those small Bluetooth speakers. So it will become like that, so that it will be so lightweight. You can put it in your backpack, charge wherever you go with a 15 ampere package, right? So we have transferred the technology to a startup which is currently getting incubated in IISc. There also we are looking for people. So if you are interested to work on next generation tech, you can contact us. So this is one of those applications, and I think I'm going to skip and come to thank you. And another thing I will tell you, the thing is that if you are in engineering, there are a lot of fantastic problems to solve, okay? And now we would like to solve things before it has been solved anywhere else. And that is only possible if you guys study and has the ambition to do something in engineering. And it is hard. It is hard. See, if you have to do this, you have to know how to do coding. You have to know how to do analog circuit design. You have to know how to do digital circuit design. You have to know thermal engineering. You have to know almost everything, right? But the thing is that somehow we have figured that engineering is not that interesting. But I don't know. It is not because I do this. But what I'm saying is that it is very rewarding if you do that, solve this kind of problems, right? And we should do that, right? Okay, thank you. Yes. So if you have any questions, you can ask. Any questions? And I'll tell you, I have been to China last year. Right? It's only people like you. They have taken the technology way beyond where Europe or US is. Okay? There are people like you and me. Nothing great. But only thing there, they have the passion. You have to have that. And you need to know that we have interesting stuff to do here, other than just, building apps and doing YouTubing. That is fine, no problem. That is also good if you can do it. But there is a lot of interesting things to do here. Okay. Questions?
One question. So you have told about the startups. So are you providing any internships for students? Because next semester students, IES students having internships.
See, I'll tell you the problem. What happens is that we have huge amount of work, we don't have people. But the thing is that some interns, they are not sincere. So they run away. Because we mean business. You come, that's fine. But you have to do work. So, but we have actually, from BMS college and few other colleges, we have seen in this startup there is one guy from BMS college. He is BTech, I think, in 2024, and then he joined us. Now he is going to work for the startup. It is very good. Possible. Anything is possible as long as you are serious about doing the work. Right? Okay. Question? All right. Thank you then.
Thank you, Dr. Kaushik Basu, sir, for this wonderful informative session. You gave us useful information about wideband gap power devices, and I personally like your session because I'm learning about power electronics this semester. So thank you so much, sir. Now I would like to call Dr. Balamurugan, sir, for certificate distribution.
Sir, during IEEE PELS Day, we have conducted some events. So we have announced the winners for that. So please do the felicitation for them, sir. So on June 20th, we have conducted IEEE PELS Day. We have conducted two events. One is quiz and another one is crossword puzzle. So out of that, we have the winners here. So I'll just call out the names, sir. Please do that. So for quiz competition, first place goes to Varshini, second year BTech student. And second place goes to Prakriti. And our next contest is crossword puzzle. So in that, first place goes to second year student Srushti. And second place goes to Veda A. And we have one more certificate for that. So in the beginning, we have created a logo design contest. So whatever the logo we have seen, that IEEE PELS and IIS logo, that was designed by our third year student, Mr. Ayush. So we'll come and collect it. Yeah, I have one more announcement. So, some of the students are IEEE members. Still, if you have not joined PELS means, those who have attended this lecture, we will give you the code. So, after this, you can fill the feedback. Only for those we provide a code. So, you can join freely for PELS Power Electronics Society. So, if you are an IEEE member, if you are other like PES, other societies, if you have joined also, if you want to join for PELS, you can scan this, and after providing the feedback, we will be able to provide the code for you. Can you do next? You can provide the feedback now. Those who are providing the feedbacks, so we will send the codes for them. So, thank you, sir. Thank you very much for your session. So, we all find like every time whenever I used to call, sir won't deny to come. And very much thankful for you, sir, for your lecture. And not only that, you have provided a lot of opportunities to the students if they take it positively, because they are also looking for the research internships next semester. I hope a group of students from this batch, they will approach you through the Power Electronics Society for that. So now I'd like to call Dr. Premkumar sir to provide a memento as a token of love to Dr. Kaushik Basu. We came to the end of our event. So, as part of the event, I would like to thank the management of DSCE for providing this opportunity to conduct the program, and also I would like to thank the IEEE PELS Power Electronics Society for positively funding our event to conduct this a great event, and also I would like to thank Dr. Premkumar, our HOD. Whenever we used to ask him for conducting any activities, he will positively approach and he will make sure that the program is conducting in the right way. Thank you very much, sir. I would also like to thank all the teaching and non-teaching faculty members, those who are providing support directly or indirectly for the conduction of event. And also I would like to thank my IEEE PELS and IIS team, because they have been the pillar of support for me to conducting the events. So many ways they are able to contribute for the conduction of the event. So lastly, I would like to thank all the students, those who are attending the session today. Thank you very much. And I would like to make one more announcement. This Saturday, we are conducting IEEE PELS and IES Student Congress 2025 in our campus this time. So it is a flagship event. I am providing the invitation to all. You can have joins together, and we have a lot of exciting events also to be there in that. So I hope all of your participation over there. Thank you.
Now I would request you all to please stand up for the national anthem.
तव शुभ नामे जागे, तव शुभ आशीष मांगे, गाहे तव जय गाथा। जनगण मंगलदायक जय हे भारत भाग्य विधाता। जय हे जय हे जय हे जय 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 हे।
Other students can have tea and snacks, and you can leave. So, IEEE society members, you please stay back. We'll have a photo, then you can leave.
ಸಾಮಾನು ಫ್ರೈ
ಲೈವ್ ಆಗ್ತಿದ್ಯಾ ಅಂತಿದೆ